Why not have special functions for upside-down trigonometry? Hey there, and welcome to How'd You Get That, where we solve all your math and physics problems. I'm David, and today we are taking a look at the reciprocal trigonometric functions, just for funsies. So we've been talking some about inverse functions recently, but it's an important distinction between inverse functions and reciprocal functions, which is what we're talking about today. Inverse functions are when we flip the outputs with the inputs of a function, but reciprocal functions are just when we flip a function on its head and take its reciprocal, which, as we'll see, is different. The issue with nomenclature here is this. We often use inverse to describe a reciprocal. It's not a coincidence that the superscript above the function notation when we're indicating an inverse function is -1. This is the same sort of notation that we use when we talk about the reciprocal of a number being that number raised to the -1 power. There's an important distinction between inverses and reciprocals. Reciprocals are multiplicative inverses, but in general, inverses are not the same thing as reciprocals. I bring this up because this week we are talking about the reciprocal trigonometric functions, cosecant, secant, and cotangent, which are the reciprocal, or 1/, of sine, cosine, and tangent, respectively. Next week, we're going to be taking a look at arcsine, arccosine, and arctangent, which are the inverses of the sine, cosine, and tangent functions. So, reciprocal trig functions, what are they? I think the easiest way to understand them is to look at them in relationship to their associated trig function. Let's start with cosecant, which is the reciprocal of sine. So remember that sine oscillates between the values -1 and 1 for every period of 2 pi. So we should expect cosecant to have a similar period, 2 pi. And in fact, it does. Notice that the sine function crosses the x-axis or has a value of 0 at intervals of pi every multiple of pi. So 0, pi, 3 pi, 4 pi, 5 pi, 6 pi, etc. Because sine is 0 at these points, we should expect its reciprocal to be undefined at those points. And in fact, the cosecant function has vertical asymptotes at multiples of pi. At the quarter periods, the sine function oscillates between -1 and 1, and we can see that the cosecant function also oscillates between -1 and 1. In fact, it touches the sine function at those points because the reciprocal of 1 is just 1, and the reciprocal of -1 is also -1. Putting this all together, we get this graph, a function that descends from infinity, hits the point 1, ascends back up to infinity, crosses a vertical asymptote all the way back down to -infinity, rises up to the point -1, and dives back down to -infinity just to start the whole process all over again. Where the sine function is equal to 1/2, the cosecant is equal to 2, and where the sine function is equal to the square root of 3 over 2, the cosecant function is equal to 2 over the square root of 3, or 2 square root of 3 over 3. We can see what secant looks like, which is the reciprocal of cosine, by remembering what happens between cosine and sine. Remember that sine is just a shift of cosine, and therefore cosine is just a shift of sine, so therefore we should expect secant to be a shift of cosecant. So if I take cosecant and shift it to the left pi over 2 units, I actually get the graph of secant. Instead of having vertical asymptotes at multiples of pi, so 0, pi, 2 pi, 3 pi, 4 pi, etc., the secant function has vertical asymptotes at odd multiples of pi over 2, so -pi over 2, pi over 2, 3 pi over 2, etc. It still has a period of pi over 2, though. And it also still touches the cosine function wherever the cosine is equal to 1 or -1. What about cotangent? Well, cotangent is just the reciprocal of tangent, so where tangent was sine over cosine, cotangent is cosine over sine. So now, wherever sine is equal to 0, the cotangent will be undefined, and wherever cosine is equal to 0, the cotangent will be equal to 0. We can see now that it has vertical asymptotes at multiples of pi, so 0, pi, 2 pi, 3 pi, 4 pi, etc. It also has a period of pi, like tangent does. Now, because this function passes from the first quadrant, x is equal to 0, into the second quadrant, where x is equal to pi over 2 to x is equal to pi, continuously, this function must be descending. or decreasing along every period. This is because in the first quadrant, we get positive values for the cotangent as well as for the tangent. And in the second quadrant, we have negative values for the cotangent and for the tangent. Cosecant, secant, and cotangent all work similarly to sine, cosine, and tangent in their own way. In the standard form, when we write it like this, we can see that A still conforms to the vertical dilation or scaling of each of these functions. For cosecant and secant, it no longer represents the amplitude, but it sort of represents the inside-out amplitude. As the sine function grows to an amplitude of, say, 2, the minimum and maximum values of the cosecant function also fall to 2 and negative 2. B is still related to the period, so B is equal to 2 pi over t, the period, for both cosecant and for secant. And for cotangent, B is equal to pi over t, where again, t is the period. C again is our phase angle, which is related to h, where h is equal to negative c over b, and h is our horizontal shift of either of these functions. K again is the vertical shift of the function. The domains and ranges of these functions get a little wonky, but if we look at, for instance, cosecant, we can see that its domain is all real numbers except for x is equal to multiples of pi. So all real numbers except x is equal to n pi, where n is an integer. Similarly, for secant, we have a domain of all real numbers except for odd multiples of pi over 2. So the domain of secant is equal to all real numbers x not equal to 2n minus 1 times pi over 2, where again, n is an integer. The domain of tangent is all real numbers except for multiples of pi, so all real numbers except x is equal to n pi and an integer. The range of secant and cosecant can be written in this way: negative infinity to k minus the absolute value of a, inclusive, union, inclusive, k plus the absolute value of a to positive infinity. And the range for cotangent is all real numbers. In the next episode, we'll be taking a look at this problem. But in the meantime, why don't you try it out yourself? The question is this: find the intersection point or points of these two functions. F of x is equal to 3/2 cosecant x minus 1, and g of x is equal to 2 sine of x plus 1. And find this for the interval from 0 to 2 pi. Try it out yourself, and I'll see you in the solution.